Hello one and all, I'm Farhan Haider and welcome to a short talk on impacts of UC formulation tightening on computation of convex hull prices. This work was jointly done by researchers at Rochester Institute of Technology and University of Connecticut. To understand our work better, let's go over the background information. The state of practice in US electricity markets is to set prices by solving the economic dispatch problems with commitment decisions fixed at optimal values from the UC problem. Although this method is easy, it however does not take into account fixed costs such as startup and no-load costs, due to which large uplift payments are required as compensation for units as they might have lost an opportunity to gain higher profits. When we do include the fixed costs, we notice that the marginal prices are not monotonically increasing with the load. As you see in the figure on the right, which shows the cost function, marginal price is slope of the cost function and it is not monotonically increasing with load. One approach to overcome this challenge is convex hull pricing. There are two ways to get the convex hull price. The first one is from the slope of the convex envelope of the total cost function. As you can see on the figure, the red curve represents the convex envelope and the slope of the red curve is monotonically increasing with the load. The slope of this curve gives you the convex hull price. However, it is very hard to obtain the convex envelope of the cost function. Another approach to calculate the convex hull prices is by using the dual variables associated with system demand constraints of the UC problem. This method suffers from convergence difficulties and long solving time. Therefore, in this talk, we take the second approach and combine it with decomposition and coordination methods and formulation tightening to overcome these challenges. We first take a decomposition coordination method called surrogate Lagrangian relaxation for fast convergence. We then introduce formulation tightening of subproblems for reduction of computational efforts. The aim of this paper is to understand the impact of formulation tightening on the computation of convex hull prices by using SLR method. Now let me go over the motivation for our approach. Up first is impacts of formulation tightening. We decided to choose formulation tightening as tight for constraints can directly delineate the convex hull of the feasible set, and the optimal solution to the LP problem is also optimal to the MILP problem. Let's consider the original formulation, which is not tight. The solution to the MILP problem is X star, and upon integer relaxation, the solution to the LP problem is this white dot. These are not same, hence we cannot use integer relaxation to get the same optimal solution. However, if the formulation is tight, represented by the red lines, the solution to the MILP as well as the LP problem is X star. Hence, we can use an LP problem to get the same optimal solution. We use the constraint vertex conversion process to get the tight formulation. You can read more about it in one of our previous studies. In practice, for the UC problem, it's very hard to develop tight formulation for 24 hours. So the goal is to obtain tightened formulations, represented by the green lines. Here the optimal solution upon integer relaxation is better than the original case, but not exactly same as the tight case. However, it is very close to the tight optimal solution. And this could give us approximate optimal solutions. For our SLR method, we chose it because it overcomes major difficulties of the traditional Lagrangian relaxation. There is no need to solve all subproblems, there is reduced multiple zigzagging, and it does not require optimal dual for convergence. We now discuss the implementation of our idea. The performance of our Titan UC formulation is compared with the conventional two-bin formulation, where both formulations are solved by the SLR method. We first considered a 3-hour example on the IEEE 118 bus dataset, whose results are shown in the table. Both MILP conventional and MILP tight gives us the convex hull prices. However, upon integer relaxation, the LP conventional does not give us convex hull prices as it produces prices that are different. But if the formulation is tight, upon integer relaxation, it can produce the same prices, which are the convex hull prices. Moving to our larger 24 example, as you can see on the figure on the right, the blue markers represent the MILP conventional prices. The orange markers show the prices from the LP conventional, and yellow markers show the prices from the LP tightened. If you notice, the yellow markers closely follow the blue markers, but the orange markers do not follow the blue markers that closely. This shows that for the 24-hour case, our tightened formulation can give us approximate comic cell prices upon integer relaxation. Conclusion. In this study, we analyzed the impact of formulation tightening on computation of convex cell prices. We did so by comparing the performance of our tightened formulation with the conventional tubing formulation and solving both formulations by surrogate Lagrangian relaxation. The testing was done on an IEEE 118 bus system, and the results show that for a 3-hour example, tight formulations can give us accurate convex cell prices upon integer relaxation. Whereas for the 24-hour example, the tightened formulation gives us approximate convex cell prices upon integer relaxation. The prices from the tightened formulation upon integer relaxation are much closer to the real CHPs than prices from the conventional formulation upon integer relaxation. This demonstrates the potential of our formulation tightening on computation of convex cell prices. These are our key references, and thank you for listening.